Hello everyone, welcome back. This is lecture 3 about computer vision. In lecture 1, we have introduced some of the basic operations of image precision, like how to change the color of that image, like into gray image, and into cool image, and into binary image, and also we have rotated that image and resized that image, and so on and so forth. However, through those operations, we're actually dealing the image as a whole. So today, we will pay more attention on its content. More specifically, we will introduce a new operation called filters or convolution, and then we will introduce the edge filters and the filters for noise reduction, and then finally we will introduce the morphological operations. Let's start with the edge detection. Edge detection is to find such kind of edges from the images. Those edges may caused by the change of depth or the surface orientation or materials or illuminations as we have introduced. Anyway, we're gonna introduce some of the filters which are able to extract such kind of edges from that image, like showing here. Okay, to start with, let me introduce the filters and convolution. What you see here is a filter, and here is an image, and both of them you can consider them as matrices, and both are with some value, and filters with some value, like showing here. We call them weights, and on the image there are some values of the pixels. If you consider the gray image, and each of them, as we have introduced, is in the range of 0 to 255. So the convolution is a process by applying this filter on that image. The process is like we every time we can consider the filter as a mask, and we put them on that image to cover a window for investigation, and then we multiply every weight with the corresponding value, like first one to the first position, and the second one for second, third one to the third, and so on and so forth, here to here and here to here. So, and then after the multiplication, we have 9, because here is a 3 by 3 filter. You could use a filter with different sizes there, but we are taking this as an example. So you have 9 multiplication results. Then you sum them together and put that results into here. That means you are get something like, let's see, here is a weight and here is a value. The weights are from here and the value are from there. So after that, you have the final value to here. And then after that, you could repeat this process like shown here. What's on the second row is actually step 2. Where you could see we have moved the filter on that image a little bit offset. It's 1 pixel. Then we repeat that process by repeating the multiplication weights to pixel values to corresponding position, and so on and so forth. It's just the same. And we apply that here, the formula, and to get the multiplication sum together, then you put them on the second position. However, you could see, because there is an offset of the filter from that image, so the original result I mean the resulting image with different size as the original image, because for some of the border pixels, we can't apply that filter. So the original result is with different sizes from the original one. You could use a technique called padding. Like we can add some 0 pixels here, and also sometimes we can add them to here, 0 pixels to enlarge virtually of the original image. So it finally will become something like this. Then after convolution, the final result can have the exact same size as the original image through that padding. Okay, with the filters and convolution in mind, so what we're gonna introduce today are all about the filters. We're changing the filter for different purpose, and then we use the same, nearly the same convolution to reach different goals. Here is a pre-width edge detector, and you can see here we have a filter with the weight as shown. And so by applying this pre-width edge detector, we can find some edges like shown here that original image. You could see what happening here is actually quite straightforward. Pre-width have two filters, one for a vertical edge like the first one, and the second is for horizontal edge detection. Then to find the edges, as I mentioned, it's quite straightforward. Let's take the first row as an example. So let's see, this filter is cover a window in the original image, like shown here, and we have some pixel values from here. Let's see, A, B, C, consecutive 3 pixels. So when we are applying the GX, the vertical edge detector, on that, it's gonna be 1. I mean, the convolution process is gonna be 1 multiply A up to 0 multiply by B. Then we add the -1 multiply by the C. Here you could see, because this one's 0, so it doesn't matter, it has been removed. So it comes out, the final result is A minus C. So by doing this, we are actually calculating the difference between the A and C, these 2 pixels. So it's like we're actually calculating the difference at the vertical direction when you apply each of the rows of this filter, because we're gonna calculating the difference between here and calculating the difference between these 2 pixels. And by repeating that process, the final result is telling us how different this column of that window from this column. So you could see once there is a vertical edges there, the difference is going to be greater than those with smaller difference. So let's take one example. See, if the ABC are just the same, that means it's a smooth region. So ABC will have the same value, something like 20, 20, 20. So A minus C here is going to be 0. And if, as I mentioned, if it's a smooth region, it's going to be 20, 20, 20. Then we have all 0 results after the filtering. However, if the difference is pretty large, like something we have 80, even 100, 100. So we got a greater result at the end. Okay, with that private, straightforward filter, and another civil is called civil filter is easy to understand. Here civil has two filters as well. One is for the vertical direction and the other is for horizontal direction. What makes it different from the private is the weight, like this at the central row or central column are given greater weights than the other two rows, and that means this filter will concentrate on those central parts more on the private filter. So that's also quite intuitive. It's applying the same principle when you're multiplying them back to the original image. It's actually calculating the difference of consecutive window, consecutive pixels. So it's but what different from private is the central difference contributes more with greater contribution to the final result, and that's also quite intuitive. And also you can apply those horizontal filter on the original image, and it will calculating the difference between this row, first row and third row. And so we'll give you the horizontal edges results. So those filters are quite similar to each other. The only difference is this concentrating more on the central part of that difference. Okay, the pre-width and the civil filters are both very intuitive. However, they actually revealed one basic principle of designing an edge detector. That is to calculating the difference. And this is you can see from the weights of that filter. They are calculating the weights, the difference between the column and rows there. However, there is one group of filter called Laplacian filters there, and here are the weights. It's not that intuitive because we can't see it's calculating the difference between rows and columns there. Actually, it's following the same principle as well. The difference is it's calculating the difference between the surrounding pixels to the central pixel. That means it's calculating the difference at different direction. So something like this, like this. So, and this is based on the assumption that one pixel has 8 neighbors. However, the second filter is with assumption like one pixel only have 4 neighbors. So it's calculating the difference at this 4 direction. So all the same, you see, to design edge detector is easy, just calculating difference. And here, Laplacian is quite convenient because it's using just one filter to calculating the difference among different directions there. It's very convenient. However, you might be interested why we're putting an 8 at the center, why we're putting a 4 at the center. So this is a little bit beyond the topic of this course. However, there might be some students who are interested in the details and the rationale behind. So we're going to introduce them. So in case you're not interested in those mathematics, you can just skip this part, and the Laplacian, you just use the Laplacian filter as it is, because you can understand it from a quite intuitive way. So the rationale behind, I mean, the mathematics actually is a derivative. You know that to calculate the change at a location, we actually use the gradients. This is an image is something like we have a plane. We have two dimensions. One is x dimension, another is y dimension. And for every pixel, we have a coordinates x and y given, and we know where it is. And we can consider the whole image as a function f x, y in this case. For any given x or y, we could have a value given by this function. So as long as we have function, we can calculate the change at each position using the gradients like f, x, y. So this is most of the time implemented by calculating the partial derivative of x, f, x at different direction. Let's just take the x direction as one example. So to simplify that problem, so it's calculating it's at x direction, the partial derivative. So it's usually implemented with the limit. That means for a given very small value epsilon approaching 0, we can calculate the value of x plus this epsilon, y here as well, and then minus fxy here, and then divided by that epsilon. However, practically epsilon is not easy to calculate, so we are using approximation by setting the epsilon to 1. So then we will have something like you will see, quite straightforward, and fx plus 1y minus fxy here. So here you could see this approximation is actually calculating the difference of 1 pixel and its neighboring next pixel here. So this is actually that part. So let's see. This is this one, and this is where it is in the original image. So we're calculating the difference between these two consecutive pixels there. By repeating this, we can actually calculating this partial derivative at all direction, like what we're showing here. So here, when we're putting every direction together, because we are repeating this process for 8 times, then we have 8 at the central part. For this, we're repeating this process 4 times, so we have a 4 here, because we're gonna subtract this one for 4 times there. Here, we're actually taking the reverse way. We're subtracting them, we're doing something like this. So it's actually the same based on the assumption of partial derivative. The only difference is we're saying sometimes we can set them as a -1 there. So it's what change the direction. Okay, so this is Laplacian filter, and that's one more last example for age detection. Okay, to make it more intuitive for programmers, let's see some code. Okay, here's an example of using filters. You don't have to worry about the code because we will provide all the code Colab notebook in our tutorial part. And you can see here to use a filter, we're taking the PIL as one example. So you have to import this to a library. So once the image was noted there, and we are converting them into a gray image, then we're applying the, here's the function, the filter on that gray image, then we have the result there. Here we're using a filter by default. So setting the filter as find the edges, then you will have the result. Quite intuitive here. You will see the edge are detected at different direction there. So, like shown here. Okay. So, let's see. We can actually using the same function by giving customized filter. Here you can see we are actually using a 3x3 filter, and we're setting the weights. Remember what the weights are? This is Laplacian filter. So we're giving a Laplacian filter, and you can see we have the result there. Laplacian filter is quite good to detect the edges at all direction because it's based on the partial derivative. Well, this is another example. Here we're using the Seibel filter. You can recognize it by the weights. You can check it back to the previous slides. Actually, they're just the same. We're using two filters separately. One is for horizontal. This is one for horizontal, and this one is for vertical there. And here's the result for horizontal detection. Here is a vertical detection. And you could see that this, you can compare this part to here. You will see that because this edge is more like horizontal, it was detected by the horizontal detector. However, to vertical detector, it's not that sensitive. This edge doesn't appear there. But here you check it out, this part. This is a vertical edge for sure, so it has been detected by the vertical detector, but it doesn't appear in the horizontal detector. I mean the result of the horizontal detector. So this result are actually telling the difference between the horizontal detection and vertical detection of using different filters. Okay, that's for edge detection. Actually, as we have introduced at the very beginning, the filters with convolution is a powerful process to dealing with the content of that images. And so it's not only for edge detection, it can be used for noise reduction as well. Let's see some example. However, to deal with the noise, we have add some noise. So we're adding some salt and pepper into that image. Here's the code. What we're doing is to generate the noise. First, you could see the name here is indicating the salt and pepper noise. So we are generating noise, and then we add that noise to that image. Then because by adding that noise, it will change the type and the range, the volume range of the original image. So we have to rescale them to make it back to the range of 0 to 255. So it will be considered as an image, so we can display that. This is what we're doing to change the type and the range, and then we could display it because back to that range, and the results shown here. And you will so go check out those pixels. You will see the noise has been added to that image. With that noise ready, and we the first filter for noise reduction, and it's also very popular, it's called the main filter. The main filter is quite straightforward as well. You could see it from the weight. Here we have something that 1/9, and so at each of the position. So what we're doing, we recall our convolution process. It's actually doing something like we are sum this weight to every pixel there. So this gives us an average of all pixels under investigation, covered by this mask under that window. So this is give the mean. So because you're giving the mean, in case the central part is some of the value which are different from the other pixels there, by taking the average, this value is some kind of will be smooth by its corresponding value, because we're actually doing a statistics to see how each part will be, how that region will be looked like by using the mean of that region. Let's see a specific example. Let's see, we have a region of 4 pixels, and the other part are all black. And the central part, we'll leave the central part as white. By calculating the mean with this filter, we will make the result, the central part will be given as more like a black, because the black color is dominating in this window rather than those white value. So that's the idea of mean filter. And here's the result. You could see here we're actually using the filter function again, but we're given a customized filter like the one we have introduced. Now here's the result. You could see that some of the noise has been reduced from the image with the noise. However, you can see it's not that perfect, and at the same time, when the noise have been reduced, the image becomes a little bit blurred there. It's not surprising indeed, because the mean actually is calculating the average. Sometimes it's missing the details from there. So to solve that problem, here is another group of filter called median filter, which are quite similar to mean but different. Here is an example. The median filter doesn't need any actual filter there. It's with very similar window under consideration, and those are not weights. They are acting values of the window under investigation. The mean filter is not taking the average to put into the central part. Rather, it will sort those values, then it will find out the median. Like here, it's actually this 11 to put it back to the central part. Here, this example is quite representative, because you could see the 80 is a value quite different from the other values. So you will see the other value was something like in this range, but the 80 is much greater than them. So in statistics, we call those outliers. By doing this, where it can the value we pick, the median, is from those majority part of that distribution, and those outlier will be eliminated from there. So this is a median filter. And you could see here is a comparison between the mean filter and the median filter. You will see the median filter, by doing that process, have a much better result than the original one. Here, we're setting them as a median filter directly. Okay, there are actually a lot of filters around, but we're not gonna introduce them all because the time limitation, and also they are actually works in a very similar way by changing different weights for different purpose, as I mentioned. But there are some recognized filters there, and they work for different noise. and like the median is considered the best for salt and pepper, and the main and Gaussian and other filters works for other noises there. This is just for your reference. When you're building an actual application, you have to try which one works the best. Okay, in addition to those filters, we're going to introduce the morphological filter as the last one we're going to introduce today. You will see from here morphological filters are not calculating the weights, not calculating multiplication of the weights. Actually, it serves like the props to the images to check out the relation between the filter and the image. And usually there are three types of relation like shown here, A, B, C. A is the structure, or AC of filter is contained exactly by the image. It's fit into the image, so that's the reason we call them fits. And B is there are some overlap between the image and this filter, like the B, this is the overlap. And C, it doesn't contain that SE here. So there's no overlap, no any overlap there. So they are the AC all filter here works like a prop, as I mentioned. Anyway, you could consider the ACE or structuring elements as filters as well, because it's actually moving the filter or SE moving on the images one by one, like what we're doing in a convolution, but it just works in different way, and it's quite useful. Um, in addition, it's usually applied to binary images because it will be better to determine if the image is contained AC or not, or to check it out if there's overlap there. So based on this, and most of the time, we'll assume that we're working on the binary images with those operations, and you will see it very soon. And here are more specifically showing different filters there. I mean, the SE filter or morphological filters there. Actually, you can use different shape because you could check the continuous of different shape inside that original image, like what's shown here is not exactly all square, rather it's star-like, cross-like images there. So this is all the SC about. So we're checking if the original image contains this shape. And here is a square. It's a quite typical one. And also there is another idea called our region. And that means which place we're putting the result back. So if it's at the center, after checking if it's fit there or it has overlap there, we will put one at the central part. For this, we will put the result here to back to the original image. So usually it doesn't matter where it is because you're gonna get very similar results no matter where you put the origin. And this is more specific way showing the volume. So usually we will put the foreground as 1 and the background as 0. And so for SE, if you check it out back to there, it's easy to compare the 0 and 1 to have the result. So if it's contained, it was contained in the original image, at that time, the window it covers should have a 0 and 1 combination, the same as the AC image. So here it's quite simple because all of them are 1, but H2 is different. It's with a cross-like. So when you are checking the back, it's easy to calculate the difference between this window and 2 that SE. So here are different combinations showing this how these two SEs fits into that original image 0, 1. So anyway, we have two relations, feeds and heats most of the time, and we're working on the binary images there. The first operation we're going to demonstrate is called erosion. The erosion is something is when we're checking out the feeds, we need the original image contains exactly the ACE we are given. So here is the result. We're using a 2x2 filter back to this original image, I mean the battery image, and here is the results. And you will see that it's like after the erosion, the object in the original image became thinner. You will see some of the details has been removed there. Like if you check out this horizontal line, it's become thinner. And for the other part, it appears the same. And if you compare them back to here, this F became thinner as well. So this is erosion. Erosion removes something from the original binary image. Let's see how it works here. So you will see here is the result. When we are comparing this region, because it contains the 3 by, here we're using 3 by 3 SE. So this part are can contain. That means the ACE can fit into that position. That means let me draw the ACE. So it will be something like all one. So because erosion is checking if it fits to this position, it fits into that position. So we will put the fit result 1 to this position. So in that case, this will be 1. So when we're repeating this process, we will continually have this position be 1, this position be 1. And for other position, it doesn't fit into there, like when we are here, the mask here. So this is will be 0 because it doesn't fit into that original image. You could see here, that's the reason the erosion actually removes some of them there, because at the edge of border of these original objects, it doesn't fit that ACE. So those parts will be removed from the original image. And it's the same when you're checking out at the border or boundary of that original objects. Those parts, they all not fit that AC. So that will be set as 0. The central value will be set as 0. It's only at the central part, like here. Let me change a different color. So it's only at those positions that ACE can fit into the original image. So it will result in those parts with 0. It will definitely become thinner from the original image. Okay, that may sound a little bit abstract for you. Let's learn this through a very specific example. So here you see we have an image, and on that image there are some values. So your job is to find out where the values are and the number of values there. So to do that, we can use those erosion. So the first thing we're doing here is actually converting the original image into a binary image that means black and white. First thing we're doing is converting them into a gray image. Then we're converting the gray image into a binary image. That process is called a thresholding. Thresholding works on a gray image. Let's see, for each of the value here we know it's in the range of 0 to 255. So we can set the threshold. Let's see, it's T. Um, um, the thresholding process works like we check um, uh, values of all the pixels, each of the pixels on that gray image. If the value is smaller than that T, we set them to 0. If that value is greater than T, that means this is if it's greater than T, and then we will set them as 255, or we can set them 1 if you're using 0, 1 image. So this is the process of thresholding. Then at the end, because its may goes into a different way, so usually we can invert that image. So we will make the objects as white and background as black. So we will have the black and white image here. So this is what it is. The original image you really seen in previous slides, and right now it's black and white. The result compared back to its original image looks good, but still you could see there are some distractions like what's shown here. Some of the details are not there, and some of the part are connected. It's not easy to count the number of that how many viruses there. So we have to do something to deal with the problem. So what we're going to do here is to use erosion to exclude the distractions. The idea is we can set SE, which are a little bit larger than those details like here, or so that part will be removed. And for some connected parts, and it will serve to break them because it's going to remove that part which are smaller than the SE. So as I mentioned, you have to try most of the time. So here we're trying a 5 by 5 SE. You could see here is the result, and we do remove some of the details, some of the distraction. At the same time, we have the break the connections there. But however, we actually, by breaking them, we created more distractions there, unfortunately. That means 5 by 5 doesn't look like a good option here. Then we tried 12 by 12. This time it works pretty well. You can see the connections are broken very well, and details are removed. And for each of them, I assume they are corresponding to one virus there. So let's just overlap this binary image back to its original image. You could see each of the dots actually hit on one virus very well. You could see here. Okay, it's right at the center of each of the virus. That means we can actually count the number of dots in that image, so we know how many viruses are actually in that image. As I mentioned, we can count the white dots. So here is a function we can actually use. It's shown here. It will help you to label with different color for each of connected parts in that image. Actually, this work not necessarily for dots. It's could work for any of the connected shape. It will assign one specific color for each of the connected part. For example, if this is connected part, it will be assigned with different color here. So after that, it returns a number like what's shown here. It's a 12. So in that case, we know there are 12 dots. Then we know there are 12 variances in that image. The result is quite good. So we know the number of variables in that image. So why not we just take a step further? Let's assume that the bigger a variance is and more infectious it is. This is something I made it up. But let's try it for fun. So can you measure how infectious each of the variables is? We can to this we can actually measure the area of each of the variables. If the area goes greater, it means it's more infectious there. So this can be done using dilation. This is another morphological filtering operation. Different from erosion, you could see from these results, dilation is not removing something, but rather adding something there. You could see this I and M are not connected, but after the dilation, it was connected. And there are, here's another example which are connected after the dilation. And most importantly, there are some holes there actually has been filled with the dilation. The reason is dilation is actually checking the overlap, the B relation of the SC to the original image. Um, so here, what's happening here, in case we have a AC, something like here, let me draw it again. That's ACE with BIOS R1. So we're gonna check if this AC is overlapped with the original image. If it's overlapped the original image, we'll set the central value as 1. Otherwise, we will set it as 0. So you will see that when the SC goes to here, here are some overlap at here. So we will set 1. That's the reason you have some of the 1s here. And especially when the AC is going to here, it's overlapped with the original image at here and here. So those parts will be set as a 1. That's the reason you will have a lot of 1s here between these two area. So it works to connect these two separate parts there. So in the first situation, it's actually adding something at the boundary part, and like to here, to here, to here. That's the reason you have those parts added to the original image. And the second situation, like I have introduced, because you're adding them at for both of the boundary, so this part will be connected. That results in this part a lot of 1s here. So this is a dilation because it's checking the overlap rather than if fits into the object completely. Okay, by using the dilation, you could see with this example, we are actually add something. This is origin. Let's see, after the erosion, we actually have the doubts at the central part, but after aiding with dilation, we covered much larger area in that image, and hopefully it covers all the variables. So you will see a new blocks covering all the variables very well here and here and here and here. So, and in that case, we could calculate the area based on this result by using AND operation. AND operation is something like we're checking the end of these two area. Let's see, this is on one, and this is second. They are within the same image but different front area. So the overlapped area, if you're using the AND, it's like the binary AND we are doing in the programming. And this area will be served to true or 1 as final image. That means we are find some region in common of these two objects. In our various case, because the mask we created with the dilation is much larger than the varus. The varus might be something here. If you're using the AND of these two images, and the varus, exact varus part will be left after the AND operation. So that's what the reason we're introducing AND operation for finding out the various region. So this is what happening. You will see here. I'm not gonna introduce the code line by line, and what we're doing is actually using the AND operation of this two. So you will see that from here, that's where the mask is, and this is the original binary image of the viruses. If we're using the AND, and what left is the virus itself. If we are using different AND for different part of that, and you will see we will find the virus one by one. So let's remain so you can see more details. So this is a roomed in value. So we are having that after dilation, the block after dilation, and we are using the AND, and it's supposed to be checked out with this part. So we have the virus exactly. And for the next one here, we are doing it to here, and then we have the virus here. And all it's saying, if it goes to here, and you have that virus left in that image. However, it's not perfect because we can't find the exact the area for some of the virus, because our blocks or sometimes has a little bit overlap there, so you will have something left there. So it's not perfect, but it's acceptable very well. So we can actually calculating the number of pixels in each of the virus. So we know the area, so we know how infectious that virus is, and that's it. And we will leave it as an assignment for you to remove those leftover that image is there. So I'm not gonna introduce the solution. We will introduce it later after the assignment. Okay, as I mentioned, we'll leave that part as an assignment for you. We will explain the solution later. Okay, actually, the erosion and dilation is two basic elementary operation for morphological operation. Most of the time, we combine them together to generate more, much more stronger filters there. For example, here is opening filter, which is indeed doing erosion first, then dilation, like what's shown here. The opening will break something, break the gaps there, like what's shown here. After the erosion, the opening, I mean, so you will see that the part are separated very well from the original image. The rationale is quite straightforward because erosion is actually remove some part, and the dilation with the same as it actually recovered some part from the original image. So it will give you something like this. By contrast, we have the closing. Closing is something you use the dilation first and then erosion. It will fill out some of the holes of the original objects, like here. You will see comparing them back to the result have been filled. The reason is when this is actually has been done for dilation to fill out the holes. However, the dilation will aid something as the outer part on the along the contour of the objects. So we can use erosion to remove that part, so you still have the contour of the original objects. Um, so something like that. However, because those part has already been filled, I mean the holes has already been filled with the one, those part will not be removed by the erosion because they can contain or fit that AC completely. So this is closing, and you can combine those dilation and erosion multiple times to create the new filters by yourself, and serve which can serve for different purposes there. Okay, thank you very much, and that's the end for lecture 3. I hope you enjoy. See you next week.